That is the example, another famous example of the brachistochrone. And the problem of brachistochrone was introduced by the younger of the Bernoulli brothers, Johann Bernoulli. In 1696. In fact, there was a competition between the two brothers as to who will solve each other's problem. So, when Jacob introduced his problem of catenary, Johann came up with the problem of brachistochrone. So, there was a rivalry among these two brothers. So, the problem says that we have to find the shape, of a wire along which a bead which is initially at rest slides from one end to the other. A bead initially at rest slides from one end to the other as quickly as possible under the influence of gravity. In short, this particular problem of brachistochrone was also termed as the optimal slippery slope problem, or optimal slippery dip. Now, there are few assumptions in this problem. Again, we assume that the curve is such that we have fixed endpoints. So, these are the assumptions in the problem, fixed endpoints, and further we assume that the motion is such that it is frictionless. That is, we do not, out of all the forces, friction does not contribute to the motion of the particle. Further, we assume that whatever we are trying to optimize or whatever solution we are trying to find, the solution is continuous and piecewise differentiable, right. Okay. Now, in fact, so popular was this problem, just a matter of trivia, so popular was this problem that it was in fact introduced in a famous Hollywood problem, that is in Spider-Man 3, where it was said by the hero Peter Parker that did Bernoulli sleep before he found the curves of quickest descent. Okay. So, in this case Peter Parker was referring to the problem of the brachistochrone, which we are going to talk about in depth over the course of our lecture. So, then the early solutions, just a little bit more trivia, the early solutions to this problem was given by Leibniz, Huygens and Newton himself, Isaac Newton, right, and then it was Euler who provided the most general framework of the class of brachistochrone problems. So, Euler provided the generalized solution to this class of problems, and finally, it was Huygens Huygens, who discovered that the motion of the problem in brachistochrone is initial condition independent. Let me denote initial condition by I dot C. So, the motion is initial condition independent. Okay. Also known as the isochrone, the so called isochrone problems. So, just a bit of setup in this problem. We see that in this case, again example 3 continued. We see that in this case that the quantity that we are trying to optimize or minimize is the total time in which the particle slides to the bottom of the curve. So, we are trying to optimize the following integral, which is the total length of the curve divided by the velocity of the curve, which is a function of the arc length itself, and the total integral of the total length is from 0 to L, and we want to minimize this particular functional. So, again L here is the length. So, let me draw a very basic figure to this problem. So, we have, let us say we have a curve and the starting point of the curve is x 0 y 0, and we have a bead which slides along this curve to come to rest at the ground level. So, let us say the total length of this curve is L, and S is the arc length of this curve, and V is the velocity, the velocity of the bead, and bead at S units down the curve, velocity of the bead at S units down the curve. Okay. So, we are not going to provide the solution at this stage, but we will look at in more depth, we will look at the solution at a later stage. Further, let me just give a bit of slightly a bit more setup of this problem. Now, we know that again in this problem we know that L is an unknown of the problem. We do not know the total length of the curve. So, to find this velocity to be substituted in this integral, we utilize the conservation of energy, right. So, the energy conservation argument states that the total energy of this system, in this case the sum of the kinetic energy plus the potential energy, is a constant of the problem. Let me denote it by C, and let us say this is equal to the value of this energy at the value of the energy at the initial point, right. So, from this argument, from this statement, I can directly find what is the value of this velocity v of x turns out to be, this is equal to, taking the right hand side equal to c, we see that this particular expression comes out to be 2 c by m minus 2 g y of x. Okay. So, let me denote this expression by 2, and we see that well, let me denote this by 3 and this particular expression by 2. So, from 2 and 3 we see that my time functional is as follows. So, my t of y is integral from x 0 to x 1 times the integrand is the arc length, which is 1 plus y prime square dx divided by square root 2 c by m minus 2 g y of x. Now, this particular integrand is quite complicated. So, we do a little bit of simplification. We substitute the following variable. Let us assume that the variable w of x is the following quantity 1 by 2 g times 2 c by m minus 2 g y, right. So, when we write this, let me call this as 3 prime. We rewrite 3 prime in terms of this variable w of x, and when we do that we get the following functional integral from x0 to x1 1 plus square root of 1 plus w prime square divided by square root of w dx. So, this is the quantity that we are trying to minimize. Of course, we have the boundary conditions which are given by y of x naught is y naught and y at x1 is y1, right. We see that, let me call this as 3 double prime. We see that 3 double prime, well, I am going to right away reveal the solution to this problem, although we are going to give a detailed step by step solution later on. So, 3 prime has a solution, has a minimal solution which is a cycloid, right. So, I am going to give a parametric representation of this cycloid which is as follows: 2 phi minus sin phi comma 2 1 minus cos phi, right. So, cycloid. Okay. Why the name cycloid? If we try to track the motion, the locus of these points on the xy plane, we see that the points are such that the locus is such that they are located at the rim of a bicycle wheel, and hence the name cycloid. Okay. So, let us move on to another example in our case study. The third example that I have in mind is the Dedeau's isoperimetric problem. The Dedeau's isoperimetric problem. Okay. So, a little bit of trivia here. So, it turns out that Dido was an ancient Egyptian queen in the early 300 BC, and she was thrown away from her empire by her wicked brother, and it turns out that she came to another land known as Carthage, and in that land the landlord gave this oust queen a piece of rope known as the bull's hide, and asked the queen to figure out an area using this rope which will be her empire, initial area of land which will be her empire. Now, it turned out that this queen was very intelligent. She figured out that the rope has to be organized in such a way that it swipes the area of the circle, and hence known as the Dedeau's isoperimetric problem. So, it turns out, so the problem is as follows. The problem is what is the shape, what is the shape of the curve which encompasses the largest area given fixed fixed length of the curve. Okay. So, in terms of the diagram, let us say that we are given a curve and we have to figure out the shape of this curve such that it encompasses the area swiped, which is the largest among all possible areas. So, it turned out that the earliest proof was given at the time of Dido herself by a Greek scientist by the name of Xanderus in 200 BC. However, the proof was very sketchy. The first version of the correct proof was given by Weierstrass himself. The first version was given by Weierstrass himself about 2000 years later. Okay. It turned out that Steiner, a German mathematician who was a contemporary of Weierstrass, also gave more proofs using contemporary of Weierstrass, also gave more proofs using the standard geometry arguments. In fact, he gave 5 more proofs. Five more proofs by geometry consideration. Okay. Now, so just to give a quick overview, in this particular case we want to maximize the area. We want to maximize the area A of y, which is the integral from x 0 to x 1 y of x dx, such that the total length in this case it is in the diagram it is L by 2, the total length, which is of course the integral of this arc length 1 plus y prime square dx, is fixed. So, this is certainly a case of isoperimetric problem, and further we assume that the solution y is continuous and piecewise differentiable, continuous and piecewise differentiable. So, well, the problem is, in this case my x 0 and x 1 are unknowns, my x 0 and x 1 are unknowns. So, let me call this particular functional and denote it by 4. So, in this case my 4, let us go to the next page. So, in this case my 4 will be represented using the arc length variable, using S, by noting the fact that ds square is dx square plus dy square, or I have that dx is, from this simple manipulation, dx is 1 minus dy by ds square times ds. So, dx is 1 minus dy by ds square times ds. So, my functional area, functional A of y in this case, now again let me redraw the figure that I had in the previous slide. Okay. So, this is my area, which is half of the total area that we are trying to optimize. So, my area is half the total integral of over the total length. Here in this case the total length here is again L by 2 of y of s. So, I am representing this functional in terms of the arc length y of s times dx, where dx is 1 minus y prime square ds. Okay. So, this is the functional that we need to optimize. Of course, Didot gave the solution to this optimal solution to this functional, and the optimal solution intuitively comes out to be a semicircle. Okay.